In this lecture, we'll talk about black holes, what it would be like to visit a black hole, and how astronomers locate black holes. White dwarfs and neutron stars are strange enough, but things can get even weirder when it comes to black holes. Let's go back to where we left off with the death of a massive star. We had a neutron star held up by neutron degeneracy pressure. If the mass of the neutron star exceeds 3 solar masses, neutron degeneracy pressure can no longer support the star against gravity. The neutron star will collapse, turning into a black hole. The idea of a black hole was predicted in the late 1800s, and to understand where the idea came from, we need to think again about escape velocity. An object of a certain mass has an escape velocity. This is the velocity you need to escape the object's gravity. On Earth, for example, you need to be moving at about 12 kilometers per second to break free of Earth's gravity. Remember, the force of gravity decreases with distance according to the inverse square law. This means if we move farther away from Earth's center of mass, gravity will be less, and the escape velocity, the velocity we need to break free of gravity, decreases. We need even less velocity if we launch from a taller tower. Now imagine what would happen if we could shrink Earth, keeping its mass the same. The smaller we make Earth, the closer the surface is to the center of mass. Therefore, gravity on the surface increases, and we'd need a larger escape velocity to break free. If you continue to shrink Earth, at some point the escape velocity will get very large. It will approach the speed of light, and when it does, nothing, not even light, can escape. If you shrink Earth down to about the size of a peanut, light would not be able to escape the surface and Earth would become a black hole. By definition, a black hole is an object whose gravity is so powerful that not even light can escape. To talk about the size of a black hole, we need to introduce the Schwarzschild Radius. This is the radius at which the escape velocity reaches the speed of light. In equation form, it's equal to 2 times the gravitational constant g times the mass of the object divided by the speed of light squared. G and c are both constants. Therefore, the Schwarzschild radius depends only on the mass of the object. The boundary between the inside of a black hole and the universe outside is called the event horizon. It's the boundary around the black hole at which the escape velocity equals the speed of light. Nothing that passes within this boundary can ever escape. The event horizon gets its name from the fact that we have no hope of learning anything about events that occur within it. We usually think of the size of a black hole as the radius of the event horizon. However, it's not really possible to measure the radius of a black hole because its center lies within the event horizon and it's not part of our universe. We therefore define the radius of a black hole as the radius it would have if geometry were flat. The radius of the event horizon is the Schwarzschild radius that we defined earlier. The structure of space and time near the event horizon is very strange. Einstein taught us that space and time are woven together into a 4-dimensional space-time. The general theory of relativity tells us that what we perceive as gravity actually arises from the curvature of space-time. It's nearly impossible to visualize 4 dimensions at once, but we can get the basic idea with a 2-dimensional analogy. Imagine a rubber sheet to represent 2-dimensional slices through space-time. In this analogy, the sheet is flat when it's far away from anything with mass. The sheet will become more curved near a massive object. Mass warps the fabric of space-time. The more massive the object, the more space-time gets warped. The curvature of space-time near a black hole is so great that the rubber sheet forms a bottomless pit. A collapsing stellar core becomes a black hole at the moment it shrinks to a size smaller than its Schwarzschild radius. The black hole still contains all the mass, but its outward appearance tells us nothing about what fell in. Therefore, black holes are the only true way to destroy information. Imagine you have a secret diary that you don't want anybody to ever read. You could burn it, but I could imagine an alien species with an intelligence great enough to reconstruct your words from the ashes and smoke particles your burnt diary created. The only way to ensure that no one ever reads your diary would be to throw it into a black hole. We have no way of answering the question of what lies inside a black hole. No information can ever emerge from within the event horizon. Because nothing can stop the crush of gravity in a black hole, all the matter that forms a black hole should be crushed to an infinitely tiny and dense point in the black hole center called a singularity. This isn't going to happen, but theoretically, what do you think would happen if our sun became a black hole? Do you think we would get sucked in? Happily, no. The only way to get sucked in is to cross the event horizon. The sun has a Schwarzschild radius of about 3 kilometers. Therefore, if the sun became a black hole, we'd have to get within 3 kilometers in order to cross the event horizon. The orbits of the planets would not change, although without the light from the sun, I doubt life on Earth would make it. Maybe the roaches would survive. I don't know. It's interesting to think about what would happen if we were to visit a black hole. So let's take an imaginary journey to a 10 solar mass black hole with a Schwarzschild radius of 30 kilometers. We can then do some experiments to test general relativity. Einstein's theory of general relativity says that time should run more slowly as the force of gravity grows stronger. It also predicts that light coming out of a strong gravitational field will be redshifted. To see how the gravity of a black hole affects time, we'll take 2 synchronized clocks from our spaceship and send one toward the event horizon of the black hole on a small shuttle. We'll see that something strange happens to the clock that is traveling toward the black hole. If we watch the clock as it moves toward the black hole, we find that it runs more slowly than our ship clock. Also, it turns red. Eventually, it's redshifted so much that we can't see it at all. You may think that the clock we sent to the event horizon had some sort of defect. Let's say you want to do your own experiment. You take another synchronized clock and head out to the event horizon yourself. Those of us on the ship put one of our clocks up to the window so you can see it as you move toward the event horizon. As you get closer to the black hole, you would notice a couple of things. First, your clock appears to be working normally. It's not slowing down or turning red for you. Second, if you look at the ship's clock, it's turning blue and it's moving faster. As you continue to approach the black hole, the force of gravity grows very strong. It will pull much harder on your feet than your head and stretch you into a spaghetti noodle. Sadly, you would not survive falling into a black hole. From the perspective of those of us on the ship, we would never actually see you cross the event horizon. From our point of view, you'll be redshifted so much that you vanish. Even if we could see you, from our perspective, your time comes to a stop. So you would appear to hover for all eternity on the edge of the event horizon. What we are observing near the black hole are the effects of general relativity. The clock near the black hole appears to slow down because of time dilation. The clock appears to turn red because of a gravitational redshift. This is a redshift due to gravity rather than due to the Doppler effect. Black holes may seem so strange that it makes sense to wonder if they really exist. And if they do, how would we find one? We can't observe black holes directly, but we can infer the presence of a black hole if it is part of a binary system. If we see a star orbiting something that we can't see, we can work out the possible mass of the objects using Newton's generalization of Kepler's laws. If the mass of the unseen companion exceeds the 3 solar mass neutron star limit, it's possible we have ourselves a black hole. Observational evidence for black holes formed by supernovae comes from studies of X-ray binaries. We learned earlier that the accretion disks around neutron stars in close binary systems can emit strong X-ray radiation, making an X-ray binary. Because a black hole has even stronger gravity than a neutron star, a black hole in a close binary system should also be surrounded by a hot X-ray emitting accretion disk. Some X-ray binaries may therefore contain black holes rather than neutron stars. One famous X-ray binary with a likely black hole is in the constellation Cygnus. And here is a table listing some likely black hole candidates. And that's all for black holes. I hope it wasn't too crazy. Take care, get yourself a coffee. I will talk to you soon.